We'll talk about Move Constructor, Move Assignment, Capacity, Reserve, Resize, and Pushback. Move Constructor addressed the issue of creating unnecessary dynamic memory and copying values from existing memory to that new memory. So we'll start with Move Constructor. Capacity, Reserve, Resize, and Pushback are functions for our simple vector class. Let's go and look at some code. So let me first of all mute this code, and we come here and we talk about the Move Constructor. We have this code here and we execute it. We go back to the code. We create a vector of 3 elements, and we want to create a new vector from this existing vector using the move function. We execute our code, and notice that the copy constructor is executed. So let's analyze what happens. And we go ahead and diagram what's happening here. So we have our stack. Size 3 elements will be at some address we've chosen, Y50 conveniently. So 53 elements here, and then we go ahead and diagram the second one. Here we have a size 3 elements. We've used Y34 000. And that one points to that one. Okay, let's analyze what happens with move. Copy assignment was executed. So copy assignment creates new memory, and then it copies elements. But in reality, we should not have to create new memory. We shouldn't have to. Instead, we should be able to simply point to that memory and invalidate that pointer. And to do that, we need the move constructor. So this is without the move constructor. Notice there's really nothing wrong if we use this for 3 elements. But if it's like 10,000 elements, then we are creating new memory to copy memory that already exists. So instead, we should just take ownership of existing memory and assign it to V1. So let's add that code to our vector, and we do that using the move constructor. So we use move constructor. The syntax, notice the double ampersand. This double ampersand is an R value. So what is an R value? So an R value little memory stack, and if we have an integer n equals 5, then this is the value 5, and here this 5 is stored at that address. We know we can get a reference to n, meaning we can say ampersand n, and we can get the reference, we can get the address of n with a reference. So then in essence, this is an L value. Literal, we cannot get the address. We cannot say &5 and get the address of 5 here. It won't allow us. So then that concept is known as an R value. Okay, an R value also exists if we have this code right here. So if we have a vector return function, get vector, and then we create the code for that vector. And we create a vector, and we return the vector. When this function finishes executing, v doesn't exist anymore. But in that instance, before it does not exist, we can use the R value, which will give us access to memory that otherwise we will not be able to access, to steal existing memory. So that's what we'll do. So this is a move constructor, and it'll be rule 4 of 5 of rule of 5 C++ 11, okay, and beyond. Let's go ahead and come here. We write code. Our constructor, make it part of the vector, but actually I didn't want to put that here. We want to put it up here, our move constructor right here. So move constructor, and our move constructor will be able to, number 1, get dynamic memory from V. Number 2, get size from V. Number 3, point V dot elements to null pointer. And finally, set V dot size to 0. So how does that code look like? Okay, we say size equals V dot size, elements equal to V dot elements, steps 1 and 2, set V dot elements to null pointer, V dot size to 0, and we've completed that piece. So now we can say, okay, so that will be our we display \n move constructor. And we execute the code again. So run the code. And notice now our code uses the move constructor. And okay, let me see, where am I not displaying output? Okay, so create an init memory, we switch pointers, and now remove from heap. So let's go and look at the code. Okay, v3 is this one right here. v1 equals move, so then when the move is occurring, then the move constructor executes, and that's when we switch the pointers, and then after return is executed, return 0, then we release memory from the heap. So with move assignment, well, maybe let me do something real quick here. Let me add some out statements to display the memory. Create memory at elements. Remember, elements prints the address. So, and we do the same thing here. Create memory at elements. We have copy assignment. Here we say copy assignment from so B2. So now we'll be pointing to a new memory. Okay, copy this one. Oops, I forgot this here. For us to make this work, I have to move this assignment in here, and I have to make it into, instead of initialization, an assignment, so equals, okay? And then we can say from elements to okay, and release memory from elements. Okay, and let's execute this code again. Run in terminal. Wrong place. Okay, right here. Let's execute it. Run in terminal. I'll create memory at CZ0. Move constructor. So instead of pointing to the new memory, we will point to existing memory, and then notice that when we release, then we are okay, right? So that's what we want. We never create new memory. We don't want to create new memory. Okay, so let's diagram this. Come here. And we create our diagram. Size 3, element Y50, this one points here, and then we have this one right here, and we have size elements. And instead of creating new memory, instead what we'll do is our move constructor is like, okay, first you point to existing memory, Y50, you are size 3, so point here, and then we invalidate this one. Don't point to Y50, point to 0 or the null pointer, and then this one is 0. And notice we didn't create memory, and that is with the move constructor. So we don't have to create additional memory, and we don't have to do unnecessary copies. And even though it's memory and it's fast, what if our vector had a lot of elements, 5,000, 10,000, then our program wouldn't be as efficient. Next, we go to move assignment. So we have this code here. Let's diagram it quickly. Well, actually, before we diagram it, let's go ahead and execute it. Let's run it to see what happens. Okay, so open main, and we label this one requires move constructor, and for now we will also comment it out, and we have this code, and we execute it. Run in terminal. I have to type it. Okay. So vector v of 3 v equals get vector. Okay. Let me make sure there's no weird characters. Okay, v3 get vector. Okay. Run in terminal. Okay, so memory created here. More memory created in the get vector. The copy assignment was executed, and remember, copy assignment creates new memory and moves memory and what have you, and we don't want to do that. So let's go ahead and diagram this piece to understand what's going on here. So we have the stack, the heap, we have this code here. So size is 3 elements. We'll stick with y50, and we have 50, 46, 42, 38, 34, 30, 26, 54. We can go ahead and label this ones here, and then we have get vector. So get vector creates a vector also. The get vector function creates a vector, right? And if you don't recall what that looks like, we can briefly look at it. Get vector, it's a free function. It creates a vector and returns it, right? So we have to take care of that. And it's of size 3, and we've been using 34 just to stay consistent. And here, so then what happens when v8 executes, right? So what happens there? And we have okay, so we know for a fact that copy assignment executed. So we go and look at the copy assignment code. Copy assignment, so new memory is created. So new memory is created. Say that new memory was created here. So new memory is created. So according to copy assignment, some new memory is created, and say it was created here. So new memory is created. How do we know that? We just follow the code. So create new memory of v.size. Copy values to the memory and delete old elements. Okay. So which elements? The v8 elements. Okay. So this values would be copied from here, right? And then we go back and look at the code. So values copied, delete elements. So this memory is deleted. Which memory? The v8 memory is deleted, and then this one is deleted, and then we point elements to temp and size to size. So then this one wouldn't point here anymore. Instead it would point to here, to y66. Size is still 3, but notice that, and then once this goes out of, once the function goes out of scope, then this one's deleted, right? But notice it doesn't seem harmful, like to create memory and copy values. But if we have a large vector, we run into the same situation again. That, I mean, we already have memory that exists here. So why not just point to it instead of, or steal it instead of creating a memory and doing moves, right? So we do that with the move assignment. And let's go ahead and understand what we're trying to do. Okay, we don't want to create a new memory, and we don't want to point to memory that we want to create. Instead, we want to say, hey, you point to this memory. It already exists, so just point to it. And get the size from this array, and then we'll invalidate this one. We'll say you point to nothing and your size is 0. That's what we're after. So we come into the last rule, and that's the move assignment, and we have to use an R value again, and we overload we do the assignment, right? So we overload the operator equals assignment. We do R value reference, and this one is move assignment 5 of 5 in rule of 5 C++ 11. Okay, and we go into the CPP, and we want to write the code for a move assignment. Move assignment. This is the class function, and then we want to say, okay, what are we going to do? We want to deallocate original dynamic memory, and then we want to get dynamic memory from V, and we want to get the size of from V, right, from V. And 4, we want to point v.elements to null pointer. 5, we want to set v.size to 0. And finally, we return a value. So let's go ahead and do that. So we go, okay, delete elements. We delete them. Get dynamic memory from V. So that means set elements equal to v.elements. Size equals v.size. Set elements v to null pointer. Set v.size to 0 and return this dereferenced. Once we do this, we can go and inspect the new diagram. So we have this, and we have here, and then we're like, okay, let's see what happens. So we have the heap and the stack. And we have some addresses here. We have V, size 3 elements, Y 50, 0, 0, 0. The vector that's created in getVector. Y 34. Okay, so we have that. You point here. And size 3. Okay, so now what happens when v equals getVector executes after it returns, right? So after it returns, we're like, okay, so we want to eliminate that memory, and we want you to point not to Y50 but to y34. And point not to y34, but to 0 or null pointer, meaning to nothing, set size to 0. And notice now, we didn't create memory. Instead, we just switched pointers, and our code is that much more efficient. And we come here to main, and we have vector v3, v equals get vector, we run it, and memory is created for v3, memory is created for the vector and the get vector. When the move assignment's created, and now we are saying that we are, instead of pointing to CZ0, we're going to point to CD8. We are going to invalidate V's original memory, set it to 0, and then we point to CD8. And when we release memory, notice that we release memory correctly, which is what we want. And now our program won't be doing unnecessary copies. And that was the move assignment. Okay, so we move on to the capacity. So the capacity, if we have a, so a capacity is not size, but space is number of elements. So we start off with a vector of 3, and we have the stack, and we have the heap, and we want to be able to say 50, 46, 42, 38, 34, 30, 26, and so forth. We diagram this one. We have the stack here. So we know size is 3. Elements points to y50. We know these ones are 0. What we want is we want to have capacity. So we want to be able to have elements that are taken up, that are used up, which is this right here. So that's the size of the vector. And then we also want to have the space of the vector. 6 slots, 3 slots. Okay. That way we can do pushbacks and not have to constantly add memory. So here we can do 1, 2, 3 pushbacks before we have to do add new memory and then copy elements to new memory. Okay, so to do that we need a reserve function and to add new memory, and we also need a resize. So resize would help us do this, but we need reserve, which will create new memory and copy values to the new memory. Okay. Resize will resize our vector, which will call resize will call reserve, which creates new memory and copies values, and resize would initialize any values beyond or greater than the size. So if we resize to 6, then we will copy 3 values, and then 1, 2, 3 more values would be initialized to 0. Okay, so let's go to our code here, and we add size of t, and we say space, and this is size plus free slots or free spaces, not free space, free spaces. Okay, and we can say, okay, size of t, capacity, const, and here we return space. Okay, that was easy. Capacity. We want to create the reserve function, which will take a size of t, and we name it new. We name that new allocation. Okay, so new allocation means like the new size and the new capacity of the vector. Okay, so come here. Let's make it part of the vector. And what does reserve do? Okay, so reserve, I'm going to copy and paste to avoid typing. I got it here. And we have make sure new allocation is greater than space. Okay, create temporary memory of size new allocation, copy values from old memory to new memory, delete the old memory arrays, set elements to temporary memory, and finally set space equals new allocation. Okay, so let's go ahead and type this code out. Number one, if new allocation less than equal to space, then we simply want to return. And notice we just return. We're not returning a data type or data. We're just saying return to exit the function. Step 2, create new memory. Pointer to integer temp equals new int new allocation. Step 3, copy values from all. Okay, so for size of ti equals 0, I less than size plus I, temp of I equals elements at I. So copying from the old memory to new memory. Delete old memory, point now to temp memory, set space equals new allocation, and that's reserve. Okay, so now we want to be able to resize a vector, and we come back here, so we want to be able to if it's 3 and we want to resize, we could, in this case space is 6, so if we would resize, we want to at least double the space so that we don't have to be doing constant new memory allocations and copies of values and initialization of values. So what we'll do is we'll say at least space times 2, and then anytime we create new memory, if the size and space are 0, if we create a vector like this, then we want it to be size and space 0 and point to nothing, right? So we'll handle that in a little bit, but for now let's go ahead and say, okay, let's say resize size of t, new allocation, and then we say, okay, let's do that. Make it part of our vector. And number 1, we want to reserve a new space of new allocation size. And then 2, initialize elements greater than size. So remember, if we create, what does this mean? So if we say we created a new allocation with space 6, then we copy these values and then we initialize these ones to 0, okay? Okay, so how do we reserve new space? Well, we simply say reserve. Reserve of new allocation. Initialize elements greater than size, so for size of ti equals size, I less than space plus I, elements at I equals 0, so initialize into 0, and that's our resize. Oh, and we have to, number 3, set space to new allocation, otherwise our space is going to be off, right? So then here we say, okay, space equals new allocation, And now we can do pushback. So when we do pushbacks, say here we have 3 elements, and then we want to say, okay, we want to do pushback. So pushback here, we do 1 pushback, 2 pushback, 3 pushbacks. On the 4th pushback, we have to add memory because size would be equal to space. Okay, so we got to take care of that. And also, if we create a vector with an empty constructor, the default constructor, we know that size, space, and elements will not be initialized to anything. So we need to take care of that first. So let's create a constructor vector, okay, like this. And we come here and we're like, okay, this is our, somebody calls the default constructor. We want to say, okay, that's fine. Initialize size to 0, space to size, and elements to null pointer. And here we'll say cout set size and space to 0, elements points to null pointer. Okay, \n, and then we'll also do the same thing here, \n, and then we can go ahead and write our pushback. So we come here and we have, okay, void push back integer some value, because we are working with integers. So we can accept an integer and add it to our elements vector. And we come here and we're like, okay, let's write pushback. And for pushback, we can say number 1, if space equal to size, add some space with default reserve default size, and 2, else if space equal, actually this is 0 and this is size, add twice space new memory, so add twice the space. And 3, add a value to element at size position and increment size by 1. Okay, let's do that. So okay, reserve default size and twice the space, let's create constants for those. So we can say, okay, const integer reserve default size 8, and then we say, oh, reserve default multiplier, set it to 2, and now we have those constants. We don't have to use literals, right? So now we can say, okay, if space equals 0, call reserve. Well, actually, we need to make this part of the vector. So make it part of the vector. Call reserve with reserve default size. So meaning create 8 new slots. Else, if space equals size, then call reserve with space times the reserve default multiplier. So multiply by 2. And then add elements at size, so the value, right? So set value to the element at size and then increment size by 1. And that's the pushback function. So if we come and say we create an empty, we create an empty vector, meaning this memory is not here. So if space is 0, then it creates 8 elements for us, and then we can do 8 pushbacks. 1, 2, 3, 4, 5, 6, 7, 8, right? So okay. Okay, what do we have to, we have this vector of 3, and then we do a pushback. Would it work? Let's look at the pushback function. Is space equals 0? No, space is not 0, because when we create the vector of 3, we are passing in a number size. So then actually here you see we need to initialize space. So I'm glad I went through that exercise. Okay, so we set it to size. Okay, so now if we do pushback, space equals 0? No. Is space equals size? Yes. Remember, we're doing a pushback for v3. Then we're like, okay, let's create new memory, and the new memory is created. We copy the 3 values to a new memory, and then we have 6, and we have 3 slots available, right? Space is 3 times default multiplier 6, so we would have this diagram here. So 1, 2, 3 free slots. So if we say pushback 4 at size, so what size? 3. 0, 1, 2, 3. So it would add it to the next slot, increment size by 1. So if we do another pushback, size is 4, 0, 1, 2, 3, 4, and we would always be pointing to the next free slot in memory. Okay, so let's go ahead and test out the code. So we have a vector empty v.pushback 4 include IOStream. Okay, it's there. A cout v add 0, and let's run this code. Run. Set size and space to 0. Okay, and then when the pushback is created, notice we didn't get a memory error, and we created new memory and we added 4. Can we add another one? So can we say v.pushback 10 and then display the element at 1? Run in terminal, and 4 and 10, so that's good. And that's it. In the next lecture we will add code to make our vectors be able to support this syntax. Alright, so we could work with integers, with double, with characters, and that part is C++ class templates. And we will do that in the next class. So that's it for today.